I am not throwing away my shot. I am not throwing away my shot. Yo, I'm just like my country. I'm young, scrappy, and hungry, and I'm not throwing away my shot.
So in this lesson, I'm going to take the concept of polar and nonpolar molecules and apply it to how molecules exist in the real world and why we should care if molecules are polar and nonpolar. And the reason why we should care is because whether a molecule is polar or nonpolar will determine what type of intermolecular force they experience. Now, an intermolecular force is simply the forces or the attractive forces between molecules. And this is different than the forces we've looked at so far, ionic bonding and covalent bonding. Ionic bonding and covalent bonding is a type of intramolecular force. So that is a force within a molecule, while an intermolecular force is an attractive force between two different molecules. All right. So we've got three different types of intermolecular forces we're going to be looking at today. We've got dipole-dipole attractions, hydrogen bonding, and then London dispersion forces. So for dipole-dipole attractions, in order for a molecule to experience dipole-dipole attractions, that molecule has to be polar. And if that molecule is polar, it will have a dipole. So keep in mind, remember, if we look at HCl, for example, since chlorine is more electronegative than hydrogen is, it will hog the electrons towards itself. So notice its dipole, which is only one dipole here, it has nothing to cancel it out going the other way, making this molecule polar. What we're going to focus on now is the fact that because chlorine is more electronegative, that's going to cause it to have a partial negative charge, which we see here, and the symbol for partial looks like this. So it's not that the electrons are completely given away to chlorine, but it's just that chlorine is hogging the electrons, making it partially negatively charged. All right. While hydrogen, because it is not hogging the electrons, it's going to be partially positively charged. It doesn't completely give up its electrons. It's still sharing electrons with chlorine, but it's going to be partially positively charged. This creates what's called a permanent dipole, right? Chlorine will always be partially negatively charged when it's with hydrogen. Hydrogen will always be partially positively charged. Negatives and positives attract. So this attraction that we see right here, that is a dipole-dipole attraction, an attraction between two different polar molecules. Now let's look at hydrogen bonding. Hydrogen bonding is a type of dipole-dipole force. However, in order to be hydrogen bonding, you need to have hydrogen as your atom that is less electronegative. And for the atom that is more electronegative, it has to be either fluorine, oxygen, or nitrogen. Okay? So just like with dipole-dipole attractions, your molecule has to be polar. And not only that, but the molecule must have hydrogen, and it must be bound to fluorine, oxygen, or nitrogen. Otherwise, it is not hydrogen bonding. All right. So if you notice here, the reason why hydrogen bonding is different than dipole-dipole, and we distinguish it, since nitrogen, oxygen, and fluorine are very electronegative, they really attract electrons well, that's going to cause their partial negative charge to be much larger than it is with just generic dipole-dipole attractions. Since they're hogging electrons so much, that's going to cause hydrogen to be really partially positively charged, so close that it's almost ionic, almost that the hydrogens give away the electrons to nitrogen, but not quite. Okay, and therefore nitrogen will be very partially negatively charged. So this attraction here looks just like dipole-dipole attractions, right? And it is, except it's stronger than dipole-dipole attractions. All right, because nitrogen is so electronegative and hydrogen is definitely not, because it's all the way over to the left. All right, so notice for a hydrogen bond, the hydrogen has to be bound to nitrogen, oxygen, or to fluorine, and then that hydrogen then has to be attracted to either fluorine, oxygen, or nitrogen. So you can see the attraction between these molecules here, between hydrogen and the nitrogen, between the hydrogen and the oxygen, and the hydrogen and the fluorine. If these hydrogens here, these three hydrogens, were not attached to an FO or N, it would not be hydrogen bonding. All right. And the last type of intermolecular force is dispersion forces, or we will often call them London dispersion forces. Okay. And for London dispersion forces, or what we will often call just LDF, okay, they will occur in any molecule and any atom. So for London dispersion forces, what happens is electrons in an atom or molecule will happen to line up in one instance on one side. And since they're kind of huddled over to this side, that will cause a partial negative charge, but it's only temporary. It'll just line up and then it'll go away again. But the important thing here is this negative charge, if it gets close to another atom, will repel the electrons from another atom, causing them to go over to this side. And if the electrons are over on this side, that'll cause a partial positive charge on this side. Well, since positives and negatives attract, there will be an attraction. Now, this is all temporary because as soon as these electrons go back to where they were floating before, you will lose that temporary dipole. And so London dispersion forces result from this temporary dipole, but since they are temporary, they are very weak. So every single molecule, every single atom experiences London dispersion forces, but because they are temporary, they are very weak, which means your London dispersion forces are going to be your weakest intermolecular force, followed by dipole-dipole forces, okay, followed by hydrogen bonding. And I'll review that again before we look at some practice problems in just a second, okay? All right, so here are 3 simulations just to show you what's happening with each of these types of intermolecular force. So for London dispersion forces, remember you've got a nonpolar molecule, so this could be oxygen, for example, 2 oxygen atoms. And when one of the molecules happens to have electrons line up, so let's watch this. Okay, they're going to get close to each other. Okay, notice that this one happens to have fewer electrons, right? And this one happens to have a greater electron cloud around it just because of how electrons move around randomly. That's going to cause this to have a partial positive charge, right? And notice as this has a partial positive charge, this is going to cause the electrons in this molecule that are evenly distributed to actually move towards this side, creating a partial negative charge here. And you can see it get even bigger. Look at that. All right. So this has a partial negative charge here because the electrons were drawn towards the partial positive side here. And this attraction here, this is a London dispersion force. Okay, so they're going to be attracted to each other, and then the electrons move back to where they were before, and that attraction is lost. And that's why we call it a temporary dipole. All right, we can see it again. Notice here, you've got electrons that are going towards this side now. They happen to go to this side, and they therefore force the electrons from this molecule to move over to this side, creating that partial negative and partial positive charge. All right, so there's that attraction, and then they go back to the way they were. All right. So that is why London dispersion forces are so weak. They happen to line up nicely. You got a partial negative and partial positive charge, but they're temporary, and then they go back. Let's now look at dipole-dipole interactions. All right, so these have permanent partial positive and partial negative charges. So let's say, for example, this was, I don't know, HCl, right? So this is the hydrogen here. This is the chloride ion. This is the chlorine atom here. They are not sharing their electrons equally. The chlorine is hogging it because it's more electronegative, causing it to have a partial negative charge and the hydrogen to have a partial positive. So as a result, the partial positive here, the hydrogen, is going to be attracted to other partial negatives. And so you can see this attraction. Oh, there's an attraction there between molecules, between them, partial negative, partial positive, and then they'll go away again. It's not a super strong attraction, but partial negative, partial positive, you see that attraction. All right, let's look at the last one for hydrogen bonding. So this is the strongest type of attraction. Okay, so again, you have a partial negative and a partial positive. This would be water, for example, oxygen here with 2 hydrogens. But because oxygen is so much more electronegative than hydrogen is, okay, that causes the partial negative to be much greater in hydrogen bonding than it is in dipole-dipole attractions. So notice they're holding on a little bit more tightly, and then they'll move off again, right? But there's a greater attraction in hydrogen bonding between the partial negative and partial positive than there is with dipole-dipole attractions. Okay, let's look at this first example here. It says identify all the intermolecular forces experienced by the following molecules. So for CO2, I've got to draw this molecule out first. Carbon has 4 valence electrons. Oxygen has 6 times 2, gives me a total of 16. All right, carbon's my central atom. So when I draw this out and make everyone happy, what you'll notice, okay, is that I am right now using too many electrons. I'm using 20, I believe. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I'm using too many, which means I need to get rid of 2 sets of lone pairs in order to create a double bond. But even when I do that, I'm using 2, 4, 6, 8, 10, 12, 14, 16, 18. I'm using too many again. So I'm going to create a second double bond and get rid of the other lone pairs of electrons. Okay, now I've got just CO2 with 2 double bonds. Okay, if you think about it, because this is going to be linear, I don't have any lone pairs of electrons on carbon pushing the oxygens downwards. Oxygen will pull this way, oxygen will pull this way, causing this molecule to be nonpolar. All right, this is a lot of work just to determine what type of intermolecular force I have. Well, if the molecule is nonpolar, the only type of attractive force it will experience is London dispersion forces. So that's my answer there. All right, let's look at SO2. Sulfur has 6 valence electrons. Oxygen has 6 as well, but there are 2 of them, so that's a total of 18 valence electrons. I'm going to do the exact same thing as I did before. Make sure everyone has an octet and is content. Okay, and when I do that, I'm using 20 valence electrons, which is too many, so I'm going to need 1 double bond. And once I use 1 double bond, when you count again, I'm actually using 18 valence electrons now, so I'm good to go. But because I've got this lone pair here, that's going to cause this structure to be bent. So it's going to look like this. And remember, this is actually a case of resonance. I really should draw, and I will very quickly, both versions. So I've got a double bond, single bond here, and then I've got a double bond, single bond on the opposite sides. Remember, those don't actually really exist. What does exist is an average. So if I average a single bond with a bond order of 1 and a double bond with a bond order of 2, that would be a bond order of 1.5. All right, I digress. So if we look at this molecule, okay, oxygen, because it's higher on the periodic table, is more electronegative than sulfur. So it'll pull down. There's nothing countering that pulling up. So your dipoles do not cancel, making this molecule polar. So if it's polar, that means, first of all, it will always experience LDF. So the question asks you to write all of the intermolecular forces it experiences. Everything experiences LDF. But then it also can experience dipole-dipole forces because it is a polar molecule, right? And oxygen will be partially negatively charged, sulfur will be partially positively charged. So if another molecule comes up and is like, oh, hey, like that, right? The sulfur will, partial positive charge on sulfur will be attracted to the partial negative on oxygen. All right, so it has dipole-dipole forces. It does not have hydrogen bonding, however, because it has no hydrogen. All right, let's look at the last one, HF. If I draw HF, I've got a total of 8 valence electrons. I'm going to draw hydrogen with a fluorine. All right, fluorine, and I'm already done. There you go. I've got 8 valence electrons. Hydrogen only wants 2. Fluorine is more electronegative than hydrogen is, which is going to cause its vector to go like that. There's its dipole. The dipoles do not cancel. Therefore, this molecule is polar. All right. Notice you do have a hydrogen bound to a fluorine here. So if you had another HF molecule off to this side, because hydrogen is so partial positively charged and fluorine has such a high partial negative charge, that attraction there between the hydrogen and fluorine with the hydrogen that is covalently bound to the fluorine, that will cause it to have hydrogen bonding, yes. And it will also have, because it is a molecule and all molecules have it, it will have LDF. Now, if you want to also say that it has dipole-dipole forces, you can, but you don't really need to because hydrogen bonding is a type of dipole-dipole force. All right, so just to write this out as a reminder, as far as intermolecular forces are concerned, in general, there are obviously going to be some exceptions, but London dispersion forces are your weakest attractive force, followed by dipole-dipole forces, followed by hydrogen bonding, which is your strongest type of intermolecular force. So hydrogen bonding is your strongest, LDF is your weakest. Well, why does that matter? Why do we care? The strength of intermolecular forces lets you know what state of matter a substance will have. So if you have a very weak intermolecular force, your substance is most likely going to be a gas at room temperature. If you've got a very strong intermolecular force, it's most likely going to be a solid at room temperature. And if you think about it, we're going to use two terms to compare intermolecular forces. We're going to use the concept of boiling point and melting point. So boiling point is the temperature at which something, a substance, boils. It becomes a gas. And melting point is the temperature at which it will become a liquid. So if you think about it, the stronger your intermolecular force, the higher the temperature will have to be in order for a substance to boil or in order for a substance to melt. So the higher or the stronger your intermolecular force, the higher your boiling or melting point. And so that's how we determine or how we compare the strength of intermolecular forces. The higher the boiling point of a substance, the stronger its intermolecular force is, right? The attraction between the molecules of that substance. So let's look at two examples here. Water is a liquid at room temperature, right? While methane is a gas. All right, so why would water be a liquid at room temperature while methane is a gas? Well, what that tells me is that the intermolecular force for water is stronger than that for methane, okay, because it is a liquid. Well, what I have to do is figure out what type of intermolecular force water has versus methane. So if I draw water, what you'll notice is that the hydrogen is attached to oxygen, okay? And so if you have multiple water molecules, what happens is that hydrogen, because it is attached to an oxygen and it has access to another oxygen, it can form an attractive force between hydrogen and oxygen, forming hydrogen bonds. And it can do that because water is polar. So this will form hydrogen bonds, while for methane, CH4, if you draw it, this molecule is nonpolar. And since it's nonpolar, if it has another methane right next to it, it will not form hydrogen bonds because the hydrogen, first of all, is not attached to oxygen, fluorine, or nitrogen. And also, since the molecule here is nonpolar, right, the dipoles cancel here, the attractive force between CH4 molecules is going to be LDF, London Dispersion Forces. So in order to explain why methane is a gas at room temperature while water is a liquid, it's because water has stronger intermolecular forces because it has hydrogen bonds, while CH4 has weaker attractive forces because it has LDF. All right, which would have a lower boiling point? All right, so NO minus, the first thing I have to do is I have to draw the Lewis structure. So NO minus, when I draw it, nitrogen has 5 valence electrons, oxygen has 6, but it's got a minus charge here, so it's got a total of 12 valence electrons. When I draw this, okay, I'm using too many valence electrons, and so what that tells me is I'm going to need to use a double bond, okay? And so this molecule here, as you can see, this is going to be a polar molecule because oxygen is more electronegative. It's going to be hogging electrons towards itself. Meanwhile, O2, if I draw this, it's got 12 valence electrons as well. That's why I'm kind of skipping this step right here. Oxygen right here is nonpolar. All right, so this is polar because its dipoles don't cancel. This is polar because its dipoles do not cancel. This is nonpolar because its dipoles do cancel, which means NO minus, okay, its attractive force is going to be dipole-dipole forces, right? Because it doesn't have hydrogen, so it can't have hydrogen bonding. Meanwhile, oxygen is going to be, since it's nonpolar, its strongest attractive force will be LDF. Okay, so which would have a lower boiling point? O2 would. Why would it? Because it has LDF and therefore its intermolecular force is weaker. Okay? So even though, when we're talking about intermolecular forces, when we're comparing water and methane, for example, here, even though water does have LDF and hydrogen bonding, we're focusing on the strongest intermolecular forces that they exhibit. So here for water and here for NO minus, even though NO minus also does exhibit London dispersion forces. All right, And the last thing here, this is comparing all the different attractive forces we might be exposed to. So here, if you notice, the very weakest attractive force in general, there are obviously going to be some exceptions, but in general is London dispersion forces. Okay, followed by dipole-dipole forces, followed by hydrogen bonding. Notice all three of these are types of intermolecular forces, so between molecules. Stronger than that is going to be your covalent bonds, which is sharing electrons. So this attractive force here, right? So that's going to be a covalent bond, which is stronger than the attractive force between molecules because now this is within a molecule. And then the absolute strongest is an ionic bond. And so when you're thinking about it, if you have an ionic compound, it's going to have an extremely high boiling point and a high melting point because its attractive forces are much stronger than those experienced by molecules that have hydrogen bonding, dipole-dipole forces, or London dispersion forces.